Okay, welcome to the fifth example in the chapter of strain. The question reads, determine the elongation of the square hollow bar when it is subjected to the axial force of 100 kilonewtons. If this axial force is increased to a force or a value of 360 kilonewtons and released, find the permanent elongation of the bar. The bar is made of a metal alloy having a stress strain diagram, which can be approximated as shown in the figure below. Okay, so right off the bat, we can find the cross-sectional area under stress since this is a column, right? So if we draw it out, do we have to draw it out? Let's draw it out. So it'll look something like this. And the cross-sectional area we are after is this stuff right here, right? If this is 50 millimeters, and this is 50 millimeters as well, this thickness right here is going to be 5 millimeters. And I can easily find the area with that diagram, and it's basically just going to be 50, the outer, 50 squared minus 40 squared, right? And this is all in millimeters. So that'll give me this cross-sectional area that is under stress. What else is the question giving me? Well, it's giving me the length of the bar, so that's probably important. That'll be my L naught when I deal with strain later on, and that is basically just 600 millimeters. We're given some information for two cases regarding the forces, and more specifically, this is kind of reaching into unknowns, but we'll deal with it now. Basically, we want to find something. Basically, in this example, the elongation when P is equal to 100 kilonewtons. So that's case one. And we want to find the elongation, or the permanent elongation, when P is equal to 360 kilonewtons. So that's case 2. Kilonewtons. Okay. Can I find anything using these two values for case 1 and case 2? Well, which I can use later on. Well, I can, because I know that sigma, in this case sigma 1, is equal to P over A, the force causing the stress over the cross-sectional area. And remember, we're going to have a normal stress here, not a shear stress. Okay, because they're perpendicular. The area and like this is coming out of the page, whereas a shear stress would be parallel to the area, right? Okay, so basically we have 100 kilonewtons, P over A, divided by 50 squared minus 40 squared in millimeters. Again, we made a mistake up here. This should be in newtons to get the proper units. So times 10 to the power of 3 newtons. This is millimeters. We can also find sigma 2. Sigma 2 is simply equal to 360 times 10 to the power of 3 newtons divided by the cross-sectional area, millimeters. Perfect stuff. Okay, once you do this calculation, again, this is force over area. That's what stress is equal to. Sorry, I didn't write it without the variables, but hopefully you don't get confused at this point, yeah? Okay, so basically you're going to get that sigma 1 is equal to 111.1 newtons per millimeter squared, which is basically megapascals. And you're going to get that sigma 2 is equal to 400 megapascals. 400 megapascals, or newtons per millimeter squared. Okay, is there anything else I can extract or put in givens? Well, there's a few other formulas, but I want to focus on this stress strain diagram a bit and see if there's any values that I can extract. Well, if I zoom in here, I immediately notice that I have this boxed out region. So, and this is linear. This is also linear, but like, why is this boxed out and why have they given me these specific values? Well, this region right here is what we call the elastic region on a stress strain diagram. And it ends at sigma yield, which is the yield stress and the yield strain, right? So what's very special, or what's so special about this elastic region? Well, let's say, for example, I apply a force right here, or I apply force and it causes a stress that is within the elastic region, right? And let's say this is 200 megapascals. What will happen? And let's say P is, for example, this stress is 200 megapascals. I apply a stress to this bar. What happens when I release that stress? Or I stop causing that stress by releasing the force? Well, it'll spring back. And by doing this, I cause a little bit of strain. So I cause a tiny bit of deformation. When I let go, it'll immediately spring back to zero, right? So no like total deformation has been caused. Okay, what if I apply a force which causes a stress that is higher than the yield stress? Let's say, for example, 300 megapascals. Okay, I apply the stress and whatnot. Let's say I let go now, and it has applied like a strain, so I have some deformation. Let's say I let go now. It will not spring back to zero. It may spring back to very close to zero, but I have caused some permanent deformation. So from this, we understand that the unique property of the elastic region is that if I apply a stress that is less than sigma yield, I'll have no permanent deformation. It'll basically spring back to zero, right? The deformation. Okay, how does this translate to our two cases, case 1 and case 2, and basically sigma 1 and sigma 2? Well, for sigma 1, this is kind of getting into unknowns, but doesn't matter. We'll explain it here. Sigma 1 is asking for the elongation of the bar, or the deformation of the bar. Whereas sigma 2 adds a word for case 2. It says, I want you to find the permanent elongation or the permanent deformation of the bar. So how does that translate to the stress strain diagram? Well, sigma 1 in this case is 111, sigma 2 is 400, right? And let's analyze sigma 1's case first. Let's say sigma 1 happens around here, right? And therefore, it'll cause epsilon 1, a strain. And this happens when I'm having the force P, and then it's causing this stress of 111 megapascals, right? What happens when I remove the force, and therefore if I remove the force, I remove the stress? What happens? Well, since it's in the elastic region, since I know that sigma 1 is less than sigma yield, it'll spring back to zero. I'll have no deformation once I let go, right? And this is basically like a rubber band, right? If I stretch the rubber band, and this is the original length, if I stretch the rubber band this distance right here, if I stretch, okay, that's a horrible diagram. If I stretch the rubber, if this is the original length of the rubber band, and then I apply a force, and then I stretch it all the way over here, if it's within its yield stress, it'll spring back to position once I remove the force, right? So this is kind of your timeline, right? And this is basically what's happening. Since it's in the elastic region, sigma 1 will not cause any permanent deformation. It'll spring back to zero, right? And this is what we call our elastic strain, or our recovery strain, basically. We're just going to have recovery strain in this case. So it's a fairly simple case and fairly simple to calculate. We'll do it in just a second once we explain the more fun one, sigma 2. Sigma 2 is a bit different. Sigma 2, as you can clearly see, if we say it's 400, sigma 2 is about here. And it's no longer within the elastic region, right? And it'll cause strain 2, right? And this is more comparable to like for example, like the spring toys when you played with, or like, I don't know if you still play with them, I don't know, pretty cool stuff. But like, basically, if this is the original length of the spring, let's say, if that's the original length, I put a force on it and I stress it way past its proper its yield stress, basically. Maybe its yield stress is about here, like that's the maximum you can pull it, but you can still continue to pull it. But what happens when I let go at this point? And let's say this is sigma yield for the spring. What happens when I let go at this point? Well, it won't go back to its original shape, right? It'll spring back, it'll spring back, but it will not go back to its original shape, right? It'll spring back, and we call this distance right here the recovery strain. We still have this recovery strain when I let go of the force, but we also have this permanent deformation, right? And we call this the permanent strain. Okay, hopefully that makes sense. How does that translate right here? So basically, if we take that example, once I let go of sigma 2, since it's past the yield point, since sigma 2 is greater than the yield stress, I'll have some spring back. Yeah, sure. Like, it'll spring back a bit, and this is my recovery strain. However, I will also have this permanent deformation, which we call permanent strain, right? So that's the idea, right? And the question, this is why it asks us to find the permanent strain, right? And how, or the permanent elongation, but we can easily find elongation from strain, right? From this, I know that epsilon 2 is equal to, just from basic addition, I know that epsilon 2 is equal to the permanent strain plus the recovery strain, right? If I rearrange this equation, I know that the permanent strain for this case is equal to epsilon 2 minus the recovery strain, right? So this is the equation I'm going to end up using later down the road. But don't worry, we'll explain that. This is just like the concept. So maybe this might have confused you more, but it's all right, So yeah. Okay. That was an explanation. Oh, there's one last thing we have to do with the stress strain diagram. It's basically, how do we characterize this linear region on the stress strain diagram? Well, we do it by looking at the slope, and we characterize the elastic region by basically calling it by its slope. And the slope in this case, as you know, is y2 minus y1 over x2 minus x1, right? In this case, y2 is 250. Actually, we won't do that. Y2 in this case is sigma yield minus 0. X2 is epsilon yield minus 0. You end up with sigma yield over epsilon yield, and basically we call this slope the elastic modulus, or Young's modulus. So that was a quick not a derivation, but explanation, right? So we characterize the elastic region by Young's modulus, which is basically stress over strain, right? So we can write that formula down as our last two things. So the elastic modulus is equal to stress over strain. And this applies to anywhere within the elastic modulus, right? Or the elastic region, because it's linear. And this entire line has the same slope. We can also add one more formula, which we forgot before, which is very important to what we're finding. Basically, it's that strain is equal to the change in length over the original length, right? Okay, unknowns. What are we looking for? We are looking for delta L for case 1, and we'll just call it delta L1, basically when P is equal to 100 kilonewtons and we let go. And we're also looking for delta, the change in length of the bar caused by the permanent deformation, which is basically the permanent change in length of the bar. We'll just call it that. And this is, just as a note, this is for case 2. Right, so when we do when we apply this force and we let go, we're gonna have some permanent deformation, as we beautifully explained up there, yeah, or I explained, yeah, beautiful stuff. Okay, so we'll do case 1 first. Actually, let's call it by name. So find delta L when P is equal to 100 kilonewtons and we let go. Okay, we start with our variable. This is fairly straightforward and simple. So we start with our variable. How can I find delta L? Well, I can use this lovely strain formula right over here. I know that delta L is equal to L naught, the original length, multiplied by the strain. What is the original length? Well, I have it at 600 millimeters. Easy stuff. What is the strain? Well, if we look at case 1 and sigma 1, we understand that it's within the elastic region, right? And if it's within the elastic region, we can use our Young's modulus formula, right? So if we branch out, we know the strain is equal to the elastic modulus multiplied by sigma, right? I have sigma 1 for case 1, right? It's just 111.1. Can I find the elastic modulus? Well, yeah, I can. It's simply just the slope of this line. We should have did it in givens, to be honest. But since it's the elastic region, I can easily find Young's modulus, right? I just have to go sigma yield over the elastic, or over strain yield, right? So it's 250 over 0.00125, right? So let's calculate that right now. And if that kind of confuses you, it's simply just the slope of this line, right? You can just replace this as m, or don't do that, but like think of it as m, right? But yeah, so this is equal to sigma yield over epsilon yield, which is equal to 250 megapascals over 0.00125 millimeters over millimeters. And from this, you're going to get that Young's modulus, or the elastic modulus, is equal to 200,000 megapascals. Okay, I know sigma yield is 111. I know that I found Young's modulus. It's basically 200 gigapascals, and I can easily complete this calculation now. So actually, let's just sub in all our numbers now. So I know that the change in length for case 1, when P is equal to 100 kilonewtons and we let go, is equal to the original length multiplied by Young's modulus multiplied by sigma 1, right? If I plug in my numbers, I get that 600 millimeters multiplied by 200,000 megapascals multiplied by 100.1 megapascals. Let's just check my calculations. Yep, it's going good. And from this, I'm going to get one of my answers. I'm going to get the elongation, right? The elongation caused by, and I think I've been saying something wrong. It's not the elongation when because I don't, like, once I apply this force, if I apply it and let go, it's going to go back to 0. So I'm not going to have any elongation. I think I've been saying that. Basically, what I mean is when I apply this force, what's my elongation, right? When I apply this force, what's my elongation right here? Because since we know, I'm looking for this delta L, right? Because when I let go of the force, it's in the elastic region, so we know it's just going to spring back to 0, which is not the case in this case too, but we'll get to that. Okay, what are you going to get for delta L? Delta L is going to be equal to 0.333 millimeters, right? Okay, beautiful stuff. That is your answer for part 1, or basically part 3 in our case. Okay, now we want to analyze case 2, right? And case 2 is a bit different. Once I apply a force on this bar of 360 kilonewtons, it's going to get into maybe this position, right? It's going to get past its yield strength. I still have to apply this force. When I let go, what's going to happen? It's going to spring back, not to 0. It's not going to spring back to 0. It's going to spring back maybe a little bit, and this is going to be our elastic strain, or our elastic or our recovery deformation, and it's going to have some permanent deformation, right? And we're looking for this permanent deformation. Okay, so we can continue with our last step, and that is basically find the permanent elongation when released from, and notice we say released here, remember, because in part, or case 1, we're looking at the deformation while we still are holding, because I think I said that before. I said we're going to apply 100 and then we're going to let go. No, we're going to apply 100 and then we're going to see the deformation, right? Because when we let go, it's going to go back to 0, right? Because it's elastic. Okay, so we're going to find the permanent deformation when released from P is equal to 360 kilonewtons. Okay, beautiful stuff. We're going to start with our variable. And what do we want to find? We want to find the permanent deformation of the bar when P is equal to 360. And that is basically equal to L naught multiplied by a strain, right? But what strain is it? Now we have like we do have 3 separate strains. We have epsilon 2, we have epsilon recovery, and we have epsilon permanent. Let me explain it one more time. I apologize, just in case, because this needs to be crystal clear before I explain anything else. Okay, so again, I'm gonna apply sigma 2, right? It's gonna cause an epsilon 2, right? If I apply stress, it's gonna cause a strain. It's not in the elastic region, so when I let go, when I stop causing this stress, what's going to happen? Let's go. I apply 360. I get this far, right? And this is my epsilon 2, right? Once I let go of this force, what's going to happen? Well, I'm going to have some elastic strain or recovery strain, right? It's going to spring back a little, but I'm also going to have this permanent strain or this permanent deformation, right? And remember, we have this formula so we can easily find like deformation. So, but it's easier to do the calculations with strain. So we'll convert to deformation at the end, simply because we have L naught. But anyway, let's go back to this diagram. What happens when I let go of this force? Well, it kind of comes to about over here, right? And what did we say? We said this is our elastic strain, and this is our permanent strain or our permanent deformation. So if I was to come up with an equation for epsilon 2, it would basically be that epsilon 2 is equal to the permanent strain plus the elastic strain or the recovery strain, right? Perfect. So when I'm trying to find the permanent elongation, what strain am I going to use? Well, I'm going to use the permanent strain, right? How do I find the permanent strain? Well, it's simply the permanent strain is equal to epsilon 2, the total strain, minus the recovery strain or the elastic strain, right? Okay, if you didn't get that, watch this back a few times, and I think I explained it before as well. So thankfully, I'm not going to explain it again. Okay, so let's write down that formula. We know that the permanent strain is equal to our total strain minus our recovery strain. Okay, and again, in this formula, we're trying to find the permanent strain. Or we're going to use the permanent strain because we want to find the permanent deformation. Do we have L naught? Yes, we do. Sorry about that. Yes, we do. Do we have the elastic strain or the permanent elastic strain? Do we have the permanent strain? Well, I know the formula for it, but I don't know it exactly. Well, epsilon 2, if I look back at the diagram, I can find by lovely linear interpolation, right? Oh, that's fun stuff. Probably do that in thermo, right? Beautiful stuff. So you're going to use linear interpolation to do that. How about the elastic strain? Well, the elastic strain or the recovery strain is simply modeled by this linear region. I'm basically assuming or pretending or not assume, basically, yeah, assuming that it's going to act similarly to the elastic region, and therefore I can simply find it by using Hooke's law, or in this case, the elastic modulus or the slope of the elastic region. So how can I find these two? This one, I can find linear interpolation. And we'll do that in case you forgot. So sorry, this video is probably going to be the longest. Yeah. Okay. How am I going to find the elastic strain? Well, it's simply, I can use, since I'm modeling it as like elastic, I can say that the recovery strain is equal to, similarly like right here, sigma 2, or the elastic modulus multiplied by sigma 2. I can quickly calculate this. So the elastic strain is equal to 200 gigapascals. I'll convert the units later, I don't have space. Multiplied by 400 megapascals. What am I going to get the strain to be? The elastic strain is going to equal, it's going to equal 0.002 millimeters per millimeter. Okay, how about this guy, or the total strain? I'll look at the diagram one last time. If I have sigma 2 right here, and I have epsilon 2 right here, epsilon 2 right here, I can find epsilon 2 because I know this point and I know this point. Let me check, or I can do it with either this point or this point. How do I do that? Well, I know that the slope of this line is the same, therefore I can use linear interpolation. How does linear interpolation work? Well, I'm basically comparing the slope. I know that m is equal to y2 minus y1 over x2 minus x1, right? Therefore, m is equal to the slope of this segment of the line right here, and this segment of the line right here are equal, right? Okay, let's do that then. So if we take sigma 2 is, well, let's just write sigma 2 minus 250. So I'm looking at this slope right here. So y2 minus y1 over x2 minus x1. right? Divided by x2 minus x1, which is 0.00125. If this is confusing you, and you know a better way to do linear interpolation, please go ahead. Okay, right? Now I'm going to compare it to this side of the, and I'm sorry I wrote the variable right here, but this is the variable I want to find, right? Let me clean this up just a bit. So again, if I compare it, I know that this is sigma 2. This is epsilon 2. I can compare the slopes of the line by saying sigma 2 I know is 400. So 400 minus 250 divided by epsilon 2 minus 0.00125 is equal, right? So this slope of the line, right, is equal to this entire slope, right? And how do I find this entire slope? Again, y2, 500, minus 250, divided by, so y2 minus y1, over x2, 0.05 minus 0.00125. x2 minus x1. And inherently, and this is the formula you use, it's going to go away in 5, 4, 3, 2, 1. And basically use that formula to find you have one unknown. You want to find sigma 2 or epsilon 2. Okay, so yeah, that's how it works. Basically, I'm comparing the slope of this part of the line with this part of the line because I know they have the same slope, right? If you do that lovely linear interpolation, you're going to get that sigma 2, and it's basically the formula that I just showed. You're going to get the epsilon 2. I keep saying sigma, I apologize. You're going to get that epsilon 2 is equal to 0.0305 millimeters per millimeter. Beautiful stuff. How do I find the permanent strain? I just subtract this number from this number. Therefore, I'm going to get that the strain, the permanent strain, is equal to 0.0305 millimeters per millimeter, right? All I have to do is multiply it by my original length, which I know L naught is equal to 600 millimeters. And let's do that right here. And finally, I get that my permanent elongation, right? My permanent elongation is equal to 600 multiplied by 0.0305 millimeters per millimeter. And that is going to give you a permanent deformation of 17. Oops, I apologize. I didn't subtract the numbers. This is incorrect. You're going to get that the permanent deformation here, or the permanent strain here, is you have to subtract the numbers. So you're going to get 0.0285. So if you multiply these two numbers together, you're going to get a permanent deformation of 17.1 millimeters. And that is your final answer. Once you apply that force of P is equal to 360 kilonewtons, and you let go, you're going to have some spring back, but it will not spring back to its original shape. It'll spring back 17.1 millimeters past like the original deformation. But yeah, that is your or these are your two answers finally to this absolutely beautiful question.